Yes, I hope that other participants will return back soon. So the third lecture for today is high energy laser plasma interactions from Jiří Vyskočil, who is an expert in scientific visualizations and programming large-scale simulations. And I hope that you like this lecture.
Good. Thank you for the introduction. Sorry. My name is Jiří Vyskočil. I am from Czech Republic, from Prague, but I currently work at the Center for Advanced Systems Understanding, which is a multidisciplinary institute under Helmholtz Zentrum Dresden-Rosendorf in Germany. And in the past, I worked as a researcher at a laser facility called Eli Beamlines in Prague. And since my lecture today will be about high-intensity laser plasma interactions, the presentation uses a lot of content that has been actually produced while I was at Eli Beamlines or by my former colleagues from Eli Beamlines. And yes, let's start. As a short overview, you can see I will talk about lasers, laser plasma interactions, and specifically applications of those interactions for electron acceleration, ion acceleration, laboratory astrophysics, and some exotic physics, exploration of unusual physical phenomena. And then specifically on about particle and cell simulations, which are I would say most common ways, most common methods to simulate those, do those large-scale simulations of laser plasma interactions, and then kind of briefly talk about examples of machine learning in particle and cell simulations. So within the framework of this school, this lecture is somewhat unusual because I'm not specifically a machine learning expert. And one of the reasons is that I'm mostly focusing on particle and cell simulations, not only in plasma physics as in my previous engagement, but now in some other scientific fields where similar methods can be applied. And while the particle and cell method itself is quite old, comes from the late 70s, and it surprisingly doesn't see much use of machine learning algorithms yet. Of course, it's an area of intensive study, and a lot of various prototypes are being made. Of course, papers are being published, but as far as I know, and I hope I'm not mistaken in this, no one is yet using those machine learning enhanced algorithms in, let's say, in production yet. So I will talk more about the physics behind this, so you have some sort of overview of a subject that might be completely new to you. Then about those most used simulations, particle and cell, and then about the challenges that those particle and cell simulations pose, and some of which could have been solved by machine learning. And like I said, people are exploring those ways, but we are not exactly there yet. Okay, so I will start from the beginning, from the tool, the basic tool we use for laser plasma interactions, and that's the laser. Probably most of you know that it's an acronym for light amplification by stimulated emission of radiation. And the the basic physical principle, this stimulated emission effect, has been predicted by Einstein already in 1917, so more than 100 years ago. It took several decades to actually use this as a light amplifier with a mirror resonator. That's what we nowadays call a laser in the 60s. And since the 60s, we've been increasing the intensity of those lasers. And you can see on this graph that the intensity increases, then kind of plateaus until the invention of the so-called chirped pulse amplification, for which Donna Strickland and Gerard Mourou have been awarded a Nobel Prize in 2018. And since then, the intensity of the actual lasers is increasing, and the like here, I know it ends at 2010, but these areas are still kind of like predicted, not reached yet. And depending on the intensity of the laser, on the focused intensity, so energy density on a surface, in the interactions with matter, which the laser is hitting, you are reaching like fundamentally qualitatively different regimes, where first you just kind of wiggle electrons still bound to the atoms in your target. Then those electrons will leave those atoms, creating plasma. And as you go to higher intensities, not only you have plasma, you have electrons with a relativistic speeds, and when you hit protons with relativistic speeds that is close to the speed of light, we talk about ultra-relativistic plasma or ultra-relativistic optics. And even higher, there's this non-linear quantum electrodynamic regime with features like vacuum break-in and electron-positron pair production, etc., which I would classify as this exotic physics part. So what is a laser? There's many different types of lasers. Most importantly, it's a source of light, and a source of light with some specific properties. So laser waves are coherent. So all waves are in phase. They're monochromatic, so they have single color, similar as LED lights. They are also polarized, so all of those coherent waves also have, we can imagine as a transverse orientation, but of course the polarization can also be circular, etc. But like they are polarized. You don't have a non-polarized laser. Specifically, when talking about laser light, we also require that the beam has a low divergence, so it's narrow, and very specifically in this context, that the beam has a high, very high intensity or luminosity. The basic principle of stimulated emission, as predicted by Einstein, is that in your amplification media, you have photons bound to atoms, and you excite that atom, thus forcing that photon to a level with a higher energy by hitting it with some other photon. So when this photon has this energy h ni, the bound electron absorbs this energy and jumps on an excited level. And after some time, it drops down, and that forces it to emit another photon with that same energy. So that way, while you are adding energy for this, sorry, you don't excite the electron by absorbing the photon. You excite the electron with some like other energy source, but that can also be, and in most cases actually is, some other source of light. But those photons come from let's say a different direction. What's important is that this incident photon with the right direction, with the right phase, forces the atom to drop, the electron to drop, and then you have two photons of the same kind, same phase, same polarization. Atom is in ground state, ready to be excited again by your energy source. Just a technicality, which I will not explain much, but it will be in the slides. It doesn't work the way I've shown, because in order for this to work, you need to reach a so-called population inversion, where you have a stable or quasi-stable system where you have more electrons on a higher energy level than on the lower energy level, and that for some reasons coming from thermodynamics cannot be achieved using a two-level system. So in reality, those systems have three or more energy levels. When you want to construct a laser, so using these theoretical ideas, what you need for a very basic one is a so-called gain medium. So that's the area where stimulated emission happens. That's where your atoms are being excited and then hit by the already existing photons. Then you need some way to feed energy to that laser, so that some way to excite those atoms to get those electrons on higher energy levels. And for that, we call that pumping. So you need some sort of pump. Most usually it's either a flash lamp, or it can be a light emitting diode. Diode lasers are better because they have a much better energy efficiency than flashlight lasers. They are more compact than flashlight lasers. So you can probably guess that they are also much more expensive than flashlight lasers. And finally, you need a resonator that provides a feedback. Now, how this works is that on one side, the resonator can be a mirror. And how it works in reality is then on one side, you would have like 100 or almost 100% reflecting mirror. And on the other side, the exit side of your laser, you have a mirror which lets about, let's say, 1% of the radiation through. So, well, actually, most of the photons that are present and freely moving in your gain medium, most of them stay there and just cycle from left to right in this resonator cavity, and this way, like they hit more of the electrons, forcing them to lower level and stimulate more of that emission. And since your cavity has some length, then also those photons that, especially initially, would go in wrong directions, they would just get absorbed at the edges of the resonator. And what gets out is this coherent light of photons that went the right path, and because of the way they were generated, they also have this same phase, same energy, etc. So this basic basic scheme was used for many years, trying different types of gain media, different sizes of resonators, ways of switching the mirror on and off actively, so that you can have the cavity closed and accumulate energy there, and at some point like leave everything out in one giant high energy pulse. And that was still not enough for reaching those extreme energy intensity levels as we're reaching nowadays. And for that, there's this chirper pulse amplification system, which I see. Sorry, I accidentally put the Czech description slide here, but you can try guessing what those parts mean. So when you have a CPA amplification system, you have some source of, well, let's say, some kind of like weak pulse, an oscillator with a very short pulse. Then when this pulse is like relatively weak, but in fact already already strong enough that maybe it might be at the threshold of what would damage your amplification crystals, because the amplification crystals, the medium for amplification is basically a similar medium as this gain medium at the beginning. So in order for this pulse to be amplified to like orders of magnitude higher energy densities, you first use this optical grid that separates individual color, like not elements, but yeah, wavelengths, and it stretches the pulse to about 1,000 times the original length of the pulse in time. So then the pulse returns, okay, on the same path back and reflects until, and now it's long. So the total energy stayed, but the maximum energy density is much lower, like this in this case, let's say 1,000 times lower. So you can safely put it through an amplifier and amplify it to this 1,000 times more. And then when you have this extremely when that pulse gain this lot of total energy, you want to compress it again. So you again use this optical grating is the correct English term here. So you again pass it through the optical grating system, but in a reverse configuration, so that it is compressed. The individual colors are again compressed back to that original pulse, and the result is an extremely short pulse with extremely high energy. And I will show a couple numbers later, but first, how we came from this small, I don't know, laser pointer or like those original lasers till those to the huge laser facilities like this one. This is this Eli Beeman's facility near Prague, where I spent 7 years of my life. And of course, okay, here you have offices and admin building, but this laser building is 3 stories high and has one more one more level underground. So it's a huge machine. On the top floor, there's cryogenic systems, power supplies, because those pulses are extremely short but deliver a lot of energy. You need a lot of condensers to accumulate the energy from the power grid and then push it into your oscillator, your gain medium, and your amplifiers. Then there are 4 laser systems installed in the ground floor, each with somewhat different properties. And those lasers are connected to the ground floor with 6 or 5 experimental halls is planned to be empty, but 5 experimental halls where you have some other machinery, target chambers where you put your target and relay your laser there. Just to get the idea of the size of this of those amplifiers. So, for example, the strongest, most powerful laser system, B-4, uses its special compressor. So that's the last part of the CPA system, where after amplification you need to compress that pulse, and that thing is I think about 2 meters high and some 8 meters long. So even like those, and it's basically just a space where you have those optical gratings that gradually compress the pulse, because it's already so powerful that it's difficult to build such a compressor that would withstand those high energy intensities. And when talking about the energy delivered, so from those 4 systems, there's this the L1 is a fast-acting system with a repetition rate of 1 kilohertz, delivering 100 megajoules in a single pulse of a 20 femtosecond long laser pulse. And if you calculate the total power, you come to 5 terawatts of peak power that is in the peak of the pulse. Of course, the pulse is extremely short, so so also the total energy is not that much. Those are, like, I would say nowadays, L2 and L3 are like typical laser systems of this kind, with 10 shots per second and with 15 to 30 femtosecond laser pulses delivering 15 to 30 joules. 15 or 30 joules is like okay, I don't know about the laws in Ukraine, but in Czech Republic, if you have a small air gun and the output power of the like the exit energy of the shot is less than 16 joules, then you don't need a gun permit for that. It's kind of like a toy, let's say. But of course, this energy is focused into an area of several micrometers. So that's the final energy density delivered on target is extremely high, depending on the exact size of the focus. And the biggest, this 10 petawatt, again, this number is the peak power. So this 10 petawatt laser can deliver 1.5 kilojoules in 1 nanosecond pulse, and 1.5 kilojoules is like a shot from some smaller machine gun, like from some AK or something. But again, you can focus with like good focusing optics, because of course, like then this concentration of power is also very high. So your focusing media, your lenses must be able to withstand that. If you focus that on an area of, again, several micrometers, you can get to energy densities of 10 to the power of 22 watts per centimeter square. That's something that's very hard to imagine, and honestly, I still haven't found a way how to properly visualize that. But like it's as if the okay, a good nuclear power plant would have something like what, 2 gigawatts, 4 gigawatts.
Gigawatt, yeah.
So to get 10 petawatt, that's still not telling you anything, because you would need to enable it just for 1 nanosecond. But like if okay, nano is 10 to 9, so we can get that gigawatt out, right? So it's so if it were operating for 1 second,
1,000 gigawatts. 1,000 gigawatts.
Yeah, 1,000. So if you operated a nuclear plant for 1,000 seconds, so 30 minutes of this of an operation of a full operation of a nuclear plant stretched into this 1 nanosecond. Again, as a power of 10 to 9, it's very difficult to like those scales are not what we're used to encounter in real life. Yeah, so those are the machines we use to shoot at different types of targets and then study what happens with those targets. And as you guessed from the title of the presentation, with this extreme energy, when you hit basically any target, you convert it to plasma. So plasma, very generally, you encounter plasmas in, I mean, plasma is the most common state of matter in the universe, actually. Not the most common state of matter on Earth, but in total in the universe, it's the one most common. You found it in solar corona, actually even in the interior of stars, in nebulas and similar space objects in the centers of heavy planets. Probably that's at least what we think. Some visible parts of the fire are also kind of plasma. And on Earth, this very nice aurora effect, which I've never seen, but I remember that in Ukraine last year, there was a day where aurora. So, more technically, so plasma is considered to be a fourth state of matter, and that's because it's kind of like hotter than a gas, and it differs from a gas that it contains free charge particles. So while in the gas you have free flying atoms, in plasma you have free flying electrons and ions, and maybe also some neutral particles. But in order for something to be classified as plasma, you need those at least some free charges. In most types of plasma, those free charges are really free. I will later show some exotic states of matter where this is not exactly true. But because of those free charges in plasma, plasma is electrically conductive, and inside plasmas, there's some collective behavior of those charges, which due to very strong electromagnetic fields that can be sustained by plasma, leads to some presence of waves. this diagram is a classification diagram of different types of plasma waves. At some point, I was able to draw it from memory. I wouldn't be able to do it now, so I wouldn't even bother you with explaining that stuff. But just that you have an idea, some of those are electron waves, some of those are ion waves, some of this explains the propagation of photons, like electromagnetic waves from the outside, and there's like different modes, whether it's a transverse wave, whether it's a longitudinal wave, and many combinations of those types. So you can see from that even and this really comes just basically from the fact that you have free charges that exhibit some collective behavior because of those strong EM fields, electromagnetic fields. And you can see that it's such a system with, let's say, kind of easy, simple rules, those basic rules, can lead to extremely complex combination of collective behavior of those visible effects, and those are what we want to study, and either in experiment or in simulations. So specifically, when we have some plasma which we want to interact with a laser, what do we mean by that? So light is a form of electromagnetic radiation. It's also a particle made of photons, but you can look at it as either waves or particles. And if we use this wave description, it's just electromagnetic radiation. And because of that, it will react or interact with charged particles. So electromagnetic waves will interact with my plasma photons, with plasma electrons or plasma ions. One thing I didn't mention in this slide is how we actually created plasma, but I said it previously. If your laser pulse is strong enough, it will actually pull out the electrons out of the atoms and free them, and in that way create the plasma through which it then propagates, or from which it will then reflect. And this is a so-called each plasma, depending on its electron density, has some and with a combination of a certain frequency of it gives you a limit called critical density. So if you have a plasma with a set density of electrons or ions, like for example we have in the ionosphere, then waves which have a frequency low enough so that those charged particles can, with their oscillation, oscillate with that frequency, so they don't need to oscillate faster, and that the frequency of the waves naturally produced in such a plasma are of frequency higher than those incoming electromagnetic waves, then those incoming electromagnetic waves will reflect. That's why this low frequency, so high wavelength radio waves reflect from the ionosphere back to Earth, and shorter waves travel outside. And you can also have it set the other way. So you have a fixed, you have a laser pulse of some known frequency, and you want to know whether your plasma target will be like transparent for it, whether the pulse will pass through. Then we talk about underdense plasma, and when the plasma density is higher, so that the pulse will be reflected back, we talk about overdense plasma. And there are various applications of those interactions of either underdense or overdense plasma. All of that, of course, depends on the exact parameters of our laser process. So I will show some basic of those interactions. So one of the ideas is to use those lasers as particle accelerators. So we can, for example, accelerate electrons. If you want to accelerate electrons, the common method is to use some underdense plasma, which is usually realized as some gas jet. So you have a gas jet, you shoot laser pulse, very short laser pulse, so that it's limited, like space limited in both directions. Again, it's a pulse, so it's not like a hard cutoff limit, but its intensity rises and drops, both in the direction of propagation. The laser pulse here propagates to the right, but also in the transverse direction. So you can look at it as kind of like a ball of light that, because of the plasma is underdense, will propagate through that medium, through that plasma. And when that happens, there's some force in effect called ponderomotive force, which forces all charged particles out of the area with like the against the high gradient of the pulse. So from the area with high intensity to the areas with low intensity. And it pushes all charged particles, like be them positively or negatively charged. But ions are much heavier than electrons, almost 2,000 times heavier. So they the laser pulse exerts the same force on each of those particles, so the ions will react much slower than the electrons. And as this laser pulse propagates through that medium, behind it, it pushes the electrons away, but the ions kind of stay in place. So there's a positively charged bubble free of electrons, which forms behind the pulse. And after a while, the electrons, which are at the edges of the bubble, will at some point be injected into the bubble and enter from this point inside the bubble and be accelerated by the laser pulse to a speed very near that of the speed of light. That's a way to make a substitute electron accelerator instead of some electromagnetic or RF long tube or accelerator ring. You can use a big laser and a gas jet. Of course, the quality of that electron beam will not be as good as the quality of the beam you get from the conventional accelerators, but the whole machine is much smaller and cheaper. So a lot of the research effort in laser plasma electron acceleration goes into enhancing this quality of the exiting beam by tuning the laser properties, by tuning the shape, for example, shaping the laser pulse and shaping the target itself, etc. If you can accelerate electrons, then of course you might ask, can I accelerate ions? The answer is yes. And the process here is much more complicated from the physical point of view. I will simplify it in that it's called target normal sheath acceleration. Target normal because it accelerates the electrons always exit in normal to the surface, so 90 degrees against the surface from which they are accelerated. And for accelerating ions, you use a overdense plasma, you use a thin foil. The foil can be like just a couple of micrometers thin, like very thin. And when you hit that foil with a laser from the backside, then some sort of so-called pre-plasma forms, and electrons are accelerated, are pulled out of the target and accelerated by the laser beam itself, and then pushed by the energy of the laser, pushed forward through the target, which kind of starts to explode. And first, those electrons expand and propagate along away from the target, and with their electric field they pull ions behind them. So in the end, some ions leave the target and are accelerated to such a speed that they will never be pulled back by those electrons. Those electrons are light, so they disperse at some point, and you are then trying to optimize your ion beam. When you go to extremely high energies of the laser, the ions can also be accelerated by the radiation, by the pressure exerted by the radiation of the laser itself. So even radiation exerts some pressure, and that's sort of obvious if you think about radiation in terms of photons and in terms of particles, which carry some momentum. So when they reflect from something, they have to give that momentum to something else, and that's so-called radiation pressure. So for extreme energies, you basically directly cut into the target foil and push those electrons out by this by the pressure of the radiation itself. So that's two basic ways to accelerate ions. And then when we can use combined effects of these to generate so-called secondary light sources to generate X-rays and gamma rays, which are, again, like laser pulse is just photons, X-rays and gamma rays are also just photons. The distinction here is in the energy of those individual photons. So from the laser beam, you have many kind of low energy photons, and through some specific interactions with the target, you convert them. The material of the target absorbs some of the incoming laser photons and emits through some different processes photons with extremely high energies. And those can be this so-called K-alpha radiation, where these photons are absorbed by electrons in atoms, which then fall back to their like basic levels, and that emits some certain spectral lines of known as K-alpha. Then okay, I talk about this, but in this so-called wave field acceleration, when you accelerate electrons, then also those electrons oscillate somehow. This is similar to this situation here in the Betatron Compton system. And those oscillating electrons, while they if they are like within the area of the laser pulse, well, with each oscillation, they will also emit some high energy photons due to break-in radiation, due to them changing an accelerating or decelerating charge emits radiation. So this is one way of getting high energy radiation. And then there's this combined concept called free electron laser, where you use this electron beam, for example, created again using a laser plasma accelerator. You get that beam, and let it pass through a series of magnets which force it. This is called an undulator. From like undulating is like making a wavy shape or path, and so those magnets force the electron to oscillate with a preset frequency by the positioning of those magnets, and again with each of the oscillation, the electron emit a photon, and those photons which are emitted in the direction of this undulator will at some point hit one of the wave crests like in front of them, and this way also act as a kind of latest stimulated emission idea. It's not stimulated emission because here you're not forcing some electron to its basic state. You're moving the electron, and that's how you emit the radiation. But this also leads to synchronized, coherent waves coming out of this system. So the result is kind of like a laser beam, but in much higher X-ray and gamma ray frequencies. That's why it's called a free electron laser. With those secondary sources, those gamma rays, those can also be produced in some other interactions, like for example when accelerating ions. I will skip that a little bit and go to those mention those extreme states of matter. That's something we call laboratory astrophysics. Laboratory astrophysics is simulating conditions which we know from space, or which we observe in space in a laboratory setting in like much smaller scale. And typically with lasers, we can achieve those high energy densities, so we can compress the matter and heat it at the same time to extreme temperatures, extreme pressures, which normally would, for example, exist only in like interiors of heavy planets, where we expect this so-called warm dense matter to most likely exist, or even interiors of stars where fusion happens due to this extreme gravitation pressure. We instead exert that pressure and temperature using lasers and hitting a small fusion fuel target about 2 millimeter big, and so we can observe that what we expect is happening in outer space, but in much smaller dimensions in laboratory. Specifically, this Warden's matter is something that deserves a mention, because that's why I said that those charges which are free might not be completely free, because there's this Warden's matter thing, which is something between a plasma and the solid phase. Not surprising, because you have solid, liquid, gas, plasma, and suddenly there's something which is almost solid and almost plasma. How it works is that this state of matter has free electrons and ions which are not really free because they're pushed together and cannot move to one another. But the electrons can travel a bit slowly, but can travel and are not bound to individual ions, but in that sense they are free. At the same time, the density of that matter is in the region of regular solid matter. So in those regions we observe many, and quantum effects might become important when some of those electrons become degenerated because they are kind of like pushed together too much. And this is what we expect in those centers of heavy planets, where this is forced by gravitation. reinforce it with lasers. And last part of the physics is the generation of electron-positron pairs, this so exotic part of physics. So where you have a laser pulse that accelerates an electron, that electron can interact with the laser field on the quantum level. It actually absorbs several of those lower energy photons from the laser field and then emit a single high energy photon in the gamma region. So that's one thing you can observe in those like extremely high fields. The other is that this gamma photon can then, through different pathways, decay into an electron and a positron. That's normally not possible because you cannot satisfy the conservation of energy and the conservation of momentum by splitting a single photon into an electron and positron pair. But when there's this high field present, there are some paths that can achieve exactly that. And when this happens, so it's not, you cannot say it's a free gamma photon that decays. It's a gamma photon that interacts with this strong laser field. So with some other photons in provided by the laser, that makes it decay into an electron and positron. And then, of course, you have an electron and positron. So those can, again, interact with this incoming laser field and produce another gamma photon that will then, again, decay into electron and positron. And that process leads to this cascade of production of electrons, positrons, and extremely high energy gamma rays until the energy of the laser pulse, which is being spent on sustaining this process, until it falls down so much that this doesn't happen. That the background energy is not enough to trigger those effects. And specifically, those effects are kind of, I mean, difficult to simulate, but maybe I would better say difficult to predict using machine learning techniques, because they are highly nonlinear and they depend on high order terms, which are like in high school physics and even in most of university level physics, those effects are usually neglected. So the goal of our simulations would be to reproduce these physical effects in silico, in a computer. So how do we do that nowadays? So in the dominant force, or neglecting the quantum effects for a while, the only force that's relevant for those plasmas, or at least laboratory plasmas, not large scale space plasmas, is where also gravitation might have some effect. In laboratory plasmas, you can of course neglect gravitation for those extremely short amounts of time. You've seen that we were talking about femtoseconds and nanoseconds. And the dominant force is the electromagnetic force. So we have charged particles that interact either with each other or with applied external fields like the laser. In order to calculate that, of course, you could just calculate the force exerted for each pair of particles, but then in order to get the evolution of that system, you need the n-squared operations in so it scales as a square of the number of particles. That's computationally expensive, and very soon you will find a problem that's unsolvable even using the biggest computers nowadays. There are statistical methods that convert those force interactions into a distribution, and you can then watch the distribution in phase space. So phase space is where you put velocity on one axis and position on the other, and study this system study the system's movement in this space. But unfortunately, this leads for those you have those 6 dimensions of 3 dimensions of space, 3 dimensions of velocity, and time has 1 dimension. So you have an equation which has 7 dimensions. That's extremely difficult to solve, of course. Another way is to treat plasma as a mix of fluids, of charged fluids, that leads to so-called magnetohydrodynamics. That's good. That allows you to simulate pretty large structures, but the derivation of magnetohydrodynamics also neglects some high-order effects which intuitively come from just a small amount of particles doing their own thing. So it kind of like smoothes those effects over. So none of these approaches, I mean, this approach is not really equivalent to this one because it loses some information. This is equivalent to this one, but it's extremely computationally intensive. So in the late 70s, scientists have come up with a method called particle and cell. It falls into broader like classification of so-called particle mesh methods. And in particle and cell, you calculate the electromagnetic fields which you discretize on a grid. So you know those fields only at the edges of those grid points. And then you have computational particles which kind of like move freely, so they can exist anywhere in that grid. And those charged particles don't interact, like computationally, don't interact directly with each other, but only through the fields of the grid. So the particle influences the movement of the particle, and its charge influences the value of the field at the grid, and in the opposite direction, the fields on the grid exert force on the particles. And this algorithm is very nice because it scales linearly with the number of particles, allowing us to make extremely large calculations, calculate large systems. And computationally, if you would, like in the limit of infinite number of particles, is equivalent to the solution of this Vlasov equation. So if you have enough particles, then yes, of course, like this, you're not sampling the phase space exactly because there's some noise around, but in a lot of cases that doesn't matter that much. And another thing you gain is that you're only sampling the full parts of the phase space, so the empty space which you would have to calculate if you were solving the Vlasov equation. With those particles, you calculate nothing, because if you have no particles, then there's nothing to compute in that area of space. The algorithm is generally composed of those 4 parts, where of course at the beginning you have some initial distribution of particles, and then you solve the equations of motion for the particles relativistically, because yeah, we're in the relativistic regime. Then from their movement, you derive the charge and current density on your grid. And from that charge and current density through Maxwell equations, you solve the value of the fields, the electric and magnetic field, then interpolate the force back to the particle. And you repeat that thousands of times. In most simulations, the part that takes most time is the Maxwell solver in case of so-called implicit solvers, or this charge and current density deposition scheme in case of explicit solvers. But whether it's this part or this part, both of them together are there to get the information of the positions and velocities of the particles to the grid and calculate the fields from that. So these two are most computationally intensive in typical particle and cell simulation. So in a sense, it's the integration of the Maxwell equations. So two partial differential equations together with some boundary conditions. That's the problem. Of course, all this can be set up in like different complex geometry configurations, or like even the basic stuff as I've shown, like those many different plasma waves that can exist. Like a typical simulation with 3D box, this would be 1 billion cells and 10 billion particles. That's really not like a huge simulation by nowadays standards. And for, let's say, 10,000 steps, which is more or less what you see here, if you start from this foil target with some microstructure, and at the front, this, I think in this calculation, this was like half 500 nanometer spheres, and you let it propagate for 10,000 steps, then at the end, you will see something like this, where you can already measure, okay, it's not really visible in this picture, but here I could already measure the exiting, the parameters of the exiting ion beam. And this is an older simulation from 2016 or 17, took about 2 days on 10,000 cores. So nowadays, of course, we have faster computers. We have at Helmholtz Centrum, there's this Picon GPU code, one of the top codes in the world, which also can use, you can guess that from the name, can use GPU to accelerate those calculations. But overall, we are still using those basic same ideas as in the 80s, with like couple algorithmic modifications, couple of tricks to make some parts somewhat faster, but I would say like not conceptually different than those traditional algorithms. And yeah, of course, we have bigger computers, faster GPUs, etc. That helps as well. And in addition to this, there's also some we're often not just interested in this basic electromagnetic interaction. So in addition to these several nanoseconds that we simulate using particle and cell, we might have some complex geometries on a larger scale, so-called pre-plasma, which forms in reality because your pulse is, yes, limited to let's say 20 femtoseconds, but it very often contains so-called pre-pulse in the length of up to picoseconds, which is maybe 8 orders of magnitude lower intensity than your main pulse. But with this intensity of, I don't know, 10 to 22 watts per centimeter squared, even those 8 orders of magnitude are still enough to actually turn those front sides of your target into plasma, which has like relatively a long time to propagate and form structures which are so long that you cannot put them in those particle in cell simulations. And on the other side of those spatial scales are quantum effects, for example, with those electron-positron pair production, where you, on the other hand, could looking at much smaller scales than is the size of your single cell, for example. So you would have to extremely enhance the resolution and like beyond what's possible to even save on the biggest computers. And with those spatial scales come also the time scales. I basically talk about all of them. So we have some atomic physics or like which happen on like extremely short time, much shorter than is your plasma time step. This pair production can also be realized on much shorter time scales, and on the longer time scales, there's this heating, for example, by the pre-pulse or like relaxation of the plasma after the pulse leaves. So combination of these is like, again, extremely difficult to integrate into those simulations and still have it calculate in some feasible time. So that's the physics, that's the simulations we use to calculate this physics. And now I will briefly show the topic you probably know better than me. So just to know what are the, I would say, like main directions where we would like to at some point sooner or later apply machine learning algorithms. So like I said, okay, I will skip this Wikipedia picture of physically informed neural network. I suppose you've already seen something like that in the previous days. But that's like, this is of course the most common one that we use when talking about enhancing particle and cell simulations, because those are targeted to solve differential equations. And in plasma physics, what I've shown, yes, that's exactly what we are solving, complex differential equations. So in order to train such a network, you put some constraints that so that it knows about the constraints coming from the form of your differential equations. Then you feed it with data either from simulations or even sometimes from experiments, and have it kind of learn how the differential equation behaves. What you want to use it for is then, let's say, enhance your field solver. In case you're using so-called implicit schemes, then each of your field integration time steps, like in an implicit scheme, you don't solve the single time step delta t with a single iteration of calculating your differential equation. You use usually some iterative scheme, which uses some preconditioning of those matrices, and that's extremely computationally intense, because you might need several thousands of iterations to solve a single time step. And amortized solvers are way of training neural networks on simulation data, and for different initial conditions, it predicts some outcomes or partial outcomes, which then help you to faster converge to the correct solution of your single time step iteration. This article from two years ago, I think, where they describe how they do it. So they map the density of electrons and the electric field together with some parameter pack into a single parameter profile, then concatenate several of these profiles into a single batch, and then run it through convolutional layers of 4 and 16 channels. Then the output of the convolutional network is flattened and put into a single or two fully connected layers before going to the output. And for 30,000 electrons, they trained them on I think several thousand different simulations, and for about 200 or 400 epochs to get that network trained, and already provide them with almost an order of magnitude increase in the like five times in the speed up in that iterative solver. And again, it's just a speed up of the iterative solver. So they're still doing this. There's still this traditional step in there. This is just helping that solver to reach the convergence faster. Another way, of course, would be to completely replace the field solver with a deep learning based solver. So again, at the beginning, you get particle positions and the electric fields, and then you really try to predict the formation of the electric fields from the like to make that single step fully only with that network. I think no, that's the slides. Yeah. Only with that single neural network, without any, let's say, traditional PDE solver step. So with this, they use the again combination of perceptron and convolutional network trained to predict the fields from the particle positions and their velocities, and they use the combination of simulation outputs and experimental data. I think it's quite interesting because normally, like on the small scale, the simulation outputs and experimental data are not a very good fit traditionally. I integrated this directly into the loop into the particle and cell loop. So after they interpolated the positions of particles to the grid values, they just use this fully neural network to completely replace this solver field solver step. It's an article from 2021. I couldn't find how much they improved since then. I suppose they did, but honestly, I don't know. Of course, this would kind of be a holy grail for these kinds of simulations, and what I know is we're still not at the holy grail yet. And the last part where deep learning is or can be or actually is employed. Oh, okay. So the results is it's in those additional algorithms or like additional physical effects that happen in your plasma. That's for those multi-scale interactions. For example, when you need to interact with a larger scale system, which can be simulated by a hydrodynamic simulation, then it's very difficult to correctly calculate what's the interaction of my boundary of small, like high resolution small cells with those big low resolution cells of that hydro simulation. Like to solve that correctly, analytically, or like numerically is extremely difficult issue. So here, but it's an interaction of like a layer of cells with one large cell. So it looks like something that should be deducible using neural networks. And of course, those additional physical effects like quantum effects in the case of gamma ray and pair production, which use completely different algorithms, come from different parts of physics than like specifically plasma physics, or some other rare events, mostly I would say from quantum physics or interaction with nuclei of heavier atoms, like heavier ions that are present in your plasma, which would be computationally prohibitive with standard methods, especially when applied to billions of particles at the same time, just to get some very rare random event. There's a kind of like an overview in this, or like this is a nice article from a group from Lisbon, and in the introduction they also provide a very nice overview of some of these specific methods that have been employed or that people tried to employ to add some advanced physics extensions to particle in cell simulations. So with that, I would end. I hope you learned something new, even if maybe not that much in the part of machine learning. At least you've seen a big part of physics that I know is usually not very well known. So just that to remember that laser plasma experiments can and often are huge. We have buildings hosting petawatt lasers, and we are simulating extreme conditions as in interiors of planets or stars. And also the simulations can be huge with multi-terabyte data sets and many days of calculations on thousands of CPUs just to get a result of one simulation, or maybe just to find out that you made a mistake when writing your input file and have to do that again. And machine learning algorithms in specifically laser plasma simulations and very specifically particle simulation is a very active but not yet fully established field. So there, all of the groups are working on something, but there's no, I would say, like no common direction that everyone would agree, oh, this is it. Most importantly, the most expensive part of those simulations, those are these particle differential equation solvers for Maxwell equations, and then additions of this multi-scale physics, be it bigger stuff, interaction with hydrodynamic simulations, or smaller stuff like production of gamma rays and electron-positron pairs. So because no one has achieved that yet, you or one of you can be the one to actually make this next step where you speed up the particle in cell algorithm by an order of magnitude, by algorithmic means, which kind of hasn't happened. I mean, like gradually it did happen since those 80s, but like this, like one step, and I'll say, oh, now it's much better. For that, the laser plasma or the particle in cell simulation scientists are waiting for like 40 years. So maybe it will be you. And if yes, I will be extremely happy to hear about it. So thank you for listening. I hope you enjoyed it.
Thank you for the lecture, but we have some questions in our Slido, so I can share my screen to show these questions. So the first question for you is, what's the best way to optimize parameters like laser intensity, pulse duration, plasma density that affect dynamics and outcomes of laser-plasma interactions?
Okay, that's a good question. I forgot to mention this, that of course there were attempts to use machine learning to optimize exactly these parameters, because it's like traditionally what you do is you have some guess, educated guess about which parameters will affect those outcomes, and then you do parameter scan exactly along those quantities. But unfortunately, as far as I know, the attempt to optimize wake field acceleration using machine learning is one of the first I've heard about. It wasn't really successful because of the sheer amount of those single simulations you would need to do to do this like backward guess. So let's say 4 years ago, this still wasn't feasible. I'm not sure how much this progressed. I've seen a short presentation about it kind of recently. So there is the people are trying to do that, but honestly, I don't remember. They were somewhat successful in that, but I cannot really quantify it. So so yeah, the best way, hard to say. I would say it's a different thing. The traditional way is to do traditional parameter scans, but yeah, you can imagine some sort of machine learning algorithm trying to make those guesses based on some difficult training, I would say.
Okay, thank you. The next question is, what are the ways to assess simulation accuracy, and how well does it reflect the reality?
Yes, that's that's again a very, very good question. Well, you really assess the accuracy of that simulation by comparing it to results of experiments. Well, you can imagine that with those extremely high energies, extremely short times, that even doing a precise measurement of the experiment is like a full scientific field on itself. The like laser plasma diagnostic methods are difficult. What they give you is sometimes just for example this so-called Schlieren photography, where you can actually get like a physical picture density variation inside plasma. So that tells you what the particle positions are, and you can directly compare that Schlieren photograph to a snapshot of your simulation. But a lot of those properties, a lot of other properties are invisible to you in an experiment. You only see them in a simulation. So in those simulations, you then very often need to kind of simulate the measurement equipment as well. So for example, you put like a virtual detector, a virtual radiation detector, a meter away from your simulated area. Guess what should be, calculate what should be on that detector, and then compare it to a real CCD detector in the interaction chamber. So really, like on this level, we compare those simulations to experiments, but with this important note that plasma diagnostics is a scientific field on itself. So getting good diagnostics is difficult. Getting good simulations is difficult. Comparing those two is somewhat. The comparison itself is easy, but the interpretation of this comparison is difficult. But just like in general, those simulations work. I would just like to quickly mention that in the 80s, this idea of this bubble acceleration of electrons was first predicted in simulations before it was actually found in a real experiment, because by the time the simulation was made, we weren't able to have a pulse that short and intensive to realize that. So those simulations work if they're done properly.
Mm-hmm. Okay, good. So the last two questions, what are the potential risks about high energy laser plasma interactions, particularly in terms of laser-induced damage to optical components and material ablation?
Yeah, yes, the risks are exactly as you say. The high intensity laser pulse itself could potentially damage your optical components that like mirrors that direct the pulse into the interaction chamber, or the focus and lenses. So you need to use tricks like similar to this chirped amplification, but instead of widening your pulse in time, you widen in transverse space while you propagating it, and then just focus it at the final point. And it might be that some of your final components will take some damage and have to be replaced. The interactions themselves can also be dangerous. You can guess that, for example, if you're interacting with an overdense target, that not only your pulse reflects back and then can potentially damage something on its way back, but also those accelerated particle bunches, if they hit your equipment, you might need to replace some lenses and stuff like this. Material ablation is not that much of a big issue, mostly because with the size of the interaction chamber, which would range between tens of centimeters up to 3 meters diameter, which is the biggest interaction chamber at EI beamlines connected to this strongest L4 laser. By the time those accelerated particles hit the walls of your chamber, they're so spread out in space that they don't really do much damage. The material ablation and damage to the chamber itself is much bigger issue in tokamaks, where you have a sustained plasma reaction, and those particles are constantly hitting your other equipment.
Thank you for the answer. And the last question for today: wouldn't electron-positron pairs annihilate with each other, generating more protons and starting the cascade event, which can go on by itself? Or is it not enough?
Okay, now I only think I understand this intuitively, and I hope I'm now not telling you some like complete nonsense. But these interactions happen in extremely strong electromagnetic fields and in large gradients of electromagnetic fields. And when you generate an electron-positron pair in such a strong field, they separate before having the chance to annihilate. They separate so much. Like in certain sense, someone once told me that this electron-positron pair production from interaction of photons is connected to kind of like to this concept of vacuum breaking, where you pull out a virtual electron-positron pair out of vacuum, and which normally, if the time for which it exists times the energy in the pair is lower than Planck constant, then it's like kind of like unobservable and nothing, like in certain way nothing happened. That those are like my understanding of virtual electron-positron pairs. And if you put them in extremely strong field, that makes them separate to a distance where they cannot annihilate anymore, then you basically pull them from being virtual to being real. But you need, again, it's not a free lunch. You need energy to do that. It happens in this extremely strong field, and that is my understanding of the reason why they don't annihilate with each other and why they propagate forwards. And then of course they then get accelerated to those like extreme velocities, and in those extreme velocities the probability of them actually like hitting each other to annihilate is absolutely negligible.
Okay, thank you for the answers, and thank you so much for such an informative lecture. Yes, goodbye, and
thank you for the invitation.
Yes, thank you. And the last lecture for today, let me maybe show my screen as